Good morning, our students, and welcome to this morning's class. Today, we'll be continuing in discussion of bivariate random variable. Do remember that in some of our previous classes, we already had introduction of bivariate random variable. We equally did discuss two types of a bivariate random variable in terms of bivariate discrete random variable and then bivariate continuous random variable. At the end of which, in also one of our previous classes, we deepened our study on the bivariate discrete random variable in terms of its probability joint, probability mass function, or what we call bivariate discrete distribution, in terms of its marginal PMF, its conditional PMF, and then we equally took some questions on them. Today, this morning, we'll be looking at squarely on the bivariate continuous random variable. Bivariate continuous random variable. Bivariate. Bivariate. Continuous random variable. Permit me to write r.v as random variable. As a way of introduction of the bivariate random variable, we begin by saying, let a random variable x and y. Let random variables x and y be continuous random variables defined on the sample space S of a random experiment. So x and y are two univariate continuous random variable defined on the sample space X of a random experiment. Let equally a function be defined this way, x, comma what, y, defined on the same sample space S of the random experiment. This function x, y is said to be a two-dimensional continuous random variable or bivariate continuous random variable. If and only if this function assigns a point on xy plane defined on this sample space of this random experiment. So this is what we call a two-dimensional continuous random variable or bivariate continuous random variable. And like we already know, especially from our previous classes, this x is a random variable, continuous random variable. This y, of course, is a continuous random variable. And because they are random variable, they have their different univariate distributions, which is, of course, univariate continuous distribution. You should also equally note that this function x, y is equally a random variable because it takes up different values from the sample space of the random experiment. And as such, it equally has its own random variable. Its own what? Distribution. And the distribution of this function, which is a bivariate continuous random variable, is what we call bivariate continuous distribution. What we call what? Bivariate continuous distribution. We call it bivariate. Bivariate continuous distribution. Bivariate continuous distribution. This bivariate continuous distribution can equally be called bivariate probability density function or the bivariate joint probability density function. So I can equally call this into be bivariate joint or equally call it a joint probability density function. So it can equally be called what? Joint probability density function. For this reason, you can find some people calling this thing to be joint. This is P, this is D, and this is what? F. And they call it a joint PDF. The last time we looked at the bivariate discrete random variable, we say that its distribution is called a joint probability mass function, called a joint PMF. So while joint PMF stands for the joint distribution of two bivariate or of bivariate discrete distribution, then the joint PMF stands for the joint distribution of bivariate continuous distribution. So while this is for continuous, this is for discrete. So that is what we call the bivariate continuous distribution or what we call the joint probability density function. How do we write the bivariate the bivariate continuous distribution? Or how do we write the joint probability density function? Permit me to clean here. We write it on the board now, and then we make some assumptions. So I will now write squarely what we call the joint PDF. Okay. The joint probability density function of a bivariate continuous random variable, say x and y, is written as f of x, comma y. If this f of x, comma y satisfies these two conditions, the first condition, number one, is f of x, comma y is greater than or equals to what? 0 for all x, comma y. That is, for all the values of x and y, which are the two random variables involved, the joint probability density function, when evaluated, is always greater than or equals to what? 0. Because probability is non-negative quantity. So it's not expected to be less than what? 0. That is what is meant by this. Okay? Then secondly, we say number 2, the integral over the range of x and integral over the range of y of f of x, comma y, the x, the y is equals to what? 1. That is to say that when this joint PDF of x and y is integrated over the range of x and over the range of what? Y, that the answer is equals to what? 1. That is to say that the entire probability of this PDF must sum to be 1. So when this distribution is written this way and it satisfies these two conditions, we can then say categorically that this function or this distribution f of x, comma y is a joint PDF of the two random variables x and y. That is what we mean by the joint PDF. Okay, we equally want to go and look at what we call the marginal probability density function, the marginal PDF, the marginal probability density function. So permit me to clean here. Talk about the marginal probability density function. Marginal probability density function. Marginal. Okay? Marginal PDF. Of course, in the marginal probability density function, our interest is that even though that we have a function that is a joint distribution of the two random variables x and y, that we want to go forward to looking at the probability distribution of each of the random variables what involved. And these two random variables now involved are x and what and y. So irrespective of the fact that we have joint PDF for x and y, we want to go and look specifically at the probability distribution of x and equally look at the probability distribution of what? Of y. That's what we mean by marginal probability distribution function. Looking at the distribution of x alone from the joint PDF, and then looking at the probability distribution of y alone from the joint PDF of x and what and y. And then this is how the marginal probability distribution function can be obtained from the joint probability density function. It is given as that f of what? Of x. This time around, you are not saying now f of x comma y because your interest alone is on f of what? Of x. That is on the probability distribution of the random variable what? X. This is given as integral over the range of what? Of y of f of x comma what? Y the what? Y. That is to say that when we want to look at the probability distribution of each of the random variable x and y, and we're interested on the probability distribution of what? Of y, that for us to arrive at that, we integrate the joint probability density function over the range of what? Of y, in order to obtain the probability distribution of the marginal probability distribution of what? Of x. So this is integrating the joint PDF now over the range of what? Y, in order to arrive at a marginal probability distribution of what? Of x. Now, if you want to talk about the marginal probability distribution of what? Of y, you say f of what? Of y, close the bracket, is given as integral over the range of what? Of x, of f of x comma what? Y, the what? The x. In the same vein, to look at the probability distribution of what? Of y, okay? We integrate now the what? The joint PDF now over the range of what? Of x, in order to obtain a marginal probability distribution of what? Of y from the joint PDF of x and y. So by then you must have been given the joint PDF, it must have been defined. So your own duty now becomes now to integrate that function given to you over the range of y for you to arrive at the marginal what? PDF of what? Of x. Then for you now, you must have been given the what? The joint PDF now. For you now to get the marginal of that of y, you integrate that function given to you now over the range of what? Of x. That's what we mean by marginal probability density function. Okay? Thank you very much. Equally permit us to clean. Let us do some introduction further before we begin to take questions. We began by looking at what we call the probability density function. One can equally talk about what is called the cumulative distribution function. There are difference between the probability density function and the cumulative density function. Do remember that for the univariate random variable, if you are told to find the CDF of what? Of x, where you have probability, yes, of what? X being less than or equals what? X. This is how you as a person can write. That is now for, in fact, you can even use this. Let us use what f, where we are saying that this x is a continuous random variable. Okay, because oftentimes when we talk about p, even though p can be used when it is continuous and p can be used when it is discrete most of the time. So, but then let us write something like this. If you are told to find, this is what we call the CDF. That is the probability that the random variable x has a value that is less than or equal to what is specific what value. And then what you are going to do in this case now, for you to get this, you are going to do integral from minus what infinity or whatever thing that is the lower bound of what of that random variable, which of course is going to be given to you of what x, okay, of f of x, the x. This is how actually you can get the CDF of a univariate continuous random variable. But this time around now we are talking about what we call the bivariate random variable. So I can equally come here and begin to talk about what we call f of what? X, less than or equals to what? X. And then we have what? That y is now less than or equals to what? Y. So this time around now we are talking about now the CDF, cumulative distribution function of a bivariate continuous random variable. So for us to now do this thing now, what is now going to happen here is we are going to say that this becomes what? Integral. Okay? From minus infinity or whatever thing that is the lower bound of what? Of x. Up to the what? To the value of what? This small x. Then integral from minus infinity to whatever thing that is the lower bound of what? Of what? Y. To this small what? Y. Of f. Of x comma what? Y. Then the what? X. The what? The y. So this is what we call the CDF of a bivariate continuous random what? Variable. Integrating now the function now, this function now, to specific values of what? Of x and what? And y. Just like we did when we had a univariate random what? Continuous random what? Variable. This is actually what we call the cumulative distribution function. The CDF of the bivariate continuous random variable, CDF. And of course, from this CDF now, we can even equally talk about what we call the marginal CDF of what? Of x and y. Marginal CDF of x and what? And y. When you talk about what marginal, what actually is going to happen is this, that you are going to have, of course, this thing I wrote here now, can equally be given as that you have what? Capital what? F. Of x comma what? Y. So we are looking at this as what? As the CDF. This is defined as, like I have earlier said here, from minus infinity to x. This equally from minus infinity to what? To x of f of x comma y dx dy. Okay? So, but when we talk about marginal now, we now begin to look at the CDF now of the different, each of the different random variables now involved, which of course in this context are x and what? And y. And in that case, you are not going to have f of x comma y here. You are now going to have only what? F of what? Either x, or you are going to have f of only y. So if you have f of only what? X, you are talking about the marginal CDF of the random variable what? X. So, and this is the same thing as I'll come here and I'll write what? F of this my x now less than or equals to what? X. Then of what? Y less than or equals to what? Infinity. I will explain what I mean by this thing. So while you are interested in when this random variable x is less than or equals to what? A particular what? Value, this random variable y is allowed to take its entire range. That's what we mean by this. It's allowed to take its entire range. Moreover, this one is not allowed to take its own entire range. This one ends at a specific value of what? Of x. Just like what we had here, x ending this place. So, and in that case now, what you're now going to have here is now going to be, you're going to have integral from minus what? Infinity to a specific value of what? Of x. And then you have what? Integral now here is now going to be from minus infinity to what? To positive infinity. You are taking the entire range of what? Of y. Entire range of what? Of y. Then you now have what we call f of x, comma y. Then you have what? You now have the x, the y. So you begin to have this kind of thing when you talk about the marginal CDF of the random variable y. That's exactly what we are talking about in the marginal CDF. The marginal CDF of the random variable x and y. Okay? Yes. The marginal CDF. Okay, then with that said, of course, we now go ahead now to talk about other things and other things we are going to talk. So in that case now, when we now talk about the marginal, we have f of we have y is now going to be f of x less than or equals to what? What we call infinity. Then we have what? Y less than or equals the specific value of what? Y, which means that we are equally going to integrate over the entire range of what? X. But when we come here, we integrate with respect to value of what? Of y. Then before we now evaluate this very quantity. Okay. So specifically, we are going to actually get back on you with respect to this. We make some confirmations with this marginal CDF. Then we get back to you. We make some confirmations about this. This, of course, holds very, very well. Yes, but we are going to make some clarification as regards with this and be able to revert back to you. Thank you very much. Let us progress. Okay. So one thing I want to mention here clearly is that in as much as we are calling this place now, we are calling here, of course, this one equally holds. We are making clarification from here to here for you. We want to make clarification from here to here. These ones. This is, of course, part of this. And like what I want to say here is that if you are told to find it, this is the marginal CDF. If you are told to find a marginal PDF, you can actually differentiate this quantity in order to arrive at the marginal PDF. You can equally differentiate it because that's exactly what we are having here. You can equally differentiate this to have this. But if you are differentiating this thing, you are differentiating it with respect to y for you to get that of x. But if you want to get this one now, you'll be differentiating with respect to x. This one you differentiate with respect to y in order to get it. This one you differentiate with respect to x. Let us not take much of your time over here. So permit me to clean this place. Okay, we now talk about what we call the conditional probability density function. That is the conditional distribution. Yes, conditional. So when you talk about the conditional PDF, you are talking about the probability of what? Of x given what? Y. Something of this nature. So this is going to be f of x comma what? Comma y, then all over f of what? Of y. That is the conditional distribution of what? Of x given y is defined as the ratio of the joint PDF now all over the marginal probability of what? Of y. Now in this case, same case now, we equally have that f of what? Of y given what? X is now going to be defined as what? What we call f of x comma what? Y all over f of what? Of x. So in this case now, you are saying that the conditional distribution of what? Of y given the value of what? Of x, or given x, is equal to the ratio of the joint PDF now all over the marginal probability density function of what? Of x. This is actually what we mean by conditional probability density function or the conditional probability distribution. Yes. Then we now talk about what we call, when do we now say that this random variable x and y are independent? When we say that they are independent. So quickly permit me to clean here. When we say they are independent. Okay. We can say that they are independent if this particular x and y, this random variable x and y, are said to be independent. They are said to be independent if this condition holds, that the f of x comma what y is the same thing as what f of x multiplied by what f of y. So when the joint PDF now of x and y transforms into the product of the marginal probability density function of x and y, then we now say that x and y are independent. Okay, so you can equally look out to see if this condition is one of it, that if f of x given y is given as what f of what of x, and then if f of y given what x will equally transform to f of what of y. That is to say that the conditional distribution of what x given what y will return the what f of what x, and the conditional distribution of what of y given x will return f of y. So by implication, this y never had effect on this x here, and because this y never had effect on this x here now, it's likely that they are independent what in nature, and the same thing applies here. So you can, most of the time, this is the major, condition for independence. But this one, I of course apply. You can confirm them by looking them up. Thank you very much. So permit me to clean this board. Let us take one or two questions quickly. Just take one or two questions. Okay. Question we are taking are already itemized here, so I'll just quickly do them out. The first question says, and I write, it said, let x and y be two random variables. This is question number one. It said, let x and y be two random variable. Permit me to write R.V as random variable. Random variables. He said then he said that f of x comma y is defined as, you have what? K into 2x plus y, then over the range of 0 less than or equals what? X, 0 less than x less than what? 1, and then 0 less than what? Y less than what? 2. Then you now have here 0x squared. 0x squared. You now say, for f of x to be a joint PDF, for f of x comma y to be a joint PDF, find k. That's the question they are giving us. Find k. So they say let x and y be two random variables, then f of x comma y defined as this over this entire range for x and y, and then 0x squared, that is outside any of this, outside this range. The value of this function should be 0. That's what they mean by 0x squared. They say for this to be a PDF, we should find the value of k. Okay, so what we are going to do is now, we now say as a way of solution, we have solution. So we have solution. So for this to be true, remember the second condition we wrote, that the joint PDF must satisfy. That condition we wrote is that integral over the range of x, integral over the range of y, of f of x comma y of the what x the y must give us what? 1. So the same thing is going to apply here, that the integration of what this function over this range must give us y, which means integral, my x begins from 0 to 1, so I have what? 0 to what? To 1. Then I have integral, it begins from what? 0 to what? To 2. I have what? 0 to what? To 2. The function I'm integrating is what? Is k into, I have what? 2 what? X plus what? Y. Then I now have what we call dx dy equals what? 1. And there's something I want to make clear here before I rearrange this. You see that the integral for that of y is inside, so it's better you integrate y first before you integrate x. And for that reason, I'm going to swap this dy to come here, so that what I have here is what we call dy dx. And for that reason, what you are now going to see me do is this. This k is a constant. And because this k is a constant, I can bring it outside this integral. And you have something like what? K coming out here. You have integral for this one, 0 to what? 1. Then I'll open a bracket like this. I'll write this function inside, which is 2 what? X plus y. I'll now close the function. Let me use this to write the function. I'll do it like this. And I'll write what? D what? Y. Then I'll now do something like this. And I'll do the x. This is equals what? Y. 1. What I'm trying to do here is, first of all, to stay inside this bracket and integrate what? Y. See my integral. Oh, permit me, sorry. So let me now open my brackets this way, and I'll do integral from 0 to what? To 2 of this quantity. So I want to stay inside this bracket now and integrate what? Integrate y before now integrating what? X. And for that reason, what I'm now going to have here becomes what? K. Then I have integral from 0 to what? To 1. I will now open my bracket. I want to integrate this quantity now with respect to what? To y. So if you come here, I am looking at this 2x to be constant because there is no y here. So what I'm going to have here becomes 2xy. So what I have that place becomes 2xy plus. Then when I come here, there is y here. To integrate this y now, I add a power here 1 again to make it 2. So what I am going to have that place becomes what? Y raised to power 2 all over what? 2. You know I am integrating it now from 0 to what? To 2. So I have what? 0 to what? To 2. You understand? Then I will now close the bracket. I will write what? The x. Because I'm yet to integrate that of what? Of x. What am I going to do here now? Wherever place I see y here, I will put 2 throughout. And wherever place I will now say minus. Wherever place I see y, I will put what? 0. So in that case now, what I'm now going to have now becomes what? I have here now to the k, then I have integral from 0 to what? To 1. I will now open a bracket here. So when y is here, so I will now put that 2 here. That 2 here will multiply this 2 here to give me 4x. So I have 4x. The sign here is what? Plus. Then here is what's my 2, because y is 2. 2 raised to power 2 is what? Is 4. Divided by this 2, it should be what? It should be 2. Then you now close the bracket and say minus. When you put 0 into all these things now, everything will result to 0. So it's as good as now cleaning this bracket now and saying what? The x. So what I'm now going to do now is now to integrate this thing now with respect to what? To x. I'm integrating now this thing now with respect to what? To x. And to integrate this with respect to x now, I am now going to come here and I will now write. Here my k is still remaining here. I say my k, I will now open my bracket this way. So, yes, I'll open my bracket this way. So here I am integrating with respect to x. So I'm going to have what is called 4x raised to power 2 plus. Here I'm going to have what is called 2 what? X. Then I will now close the bracket. I'm integrating from 0 to what? 1. 0 to what? 1. This is equals to what? 1. So what I'm going to do is wherever place I see x, I will now put what? 1 there. You understand? And that case, what I'm now going to do is now going to be, I have my k, I open a bracket. Putting 1 here, 1 squared will give me what? 4. So I have now 4 plus. Then putting 1 here will now give me 1. So 2 times 1 will give me what? 2. This is expected to give me what? 1. Okay? So this plus this will give me what? 6. So I have 6k is equals 1, and therefore my k is equals 1 over 6. Let me check what we had in the book when we integrated. Wow, we had 1 over 4. So let us quickly know what happened. We had 1 over 4. Yes, it is 1 over 4 because when you integrate here now, integrating here now, is raised to power what? 2. You have all over what? 2. Sorry for that. Integrating this thing now, you have 1 over 2. So that will cancel this and give you now 2x. And give you now 2x. So what I have here is what? 2x. Sorry about that. What I have here is 2x. So sorry about that. What I have here is 2x. So for that reason now, if you now bring that 1 here, it becomes 1 raised to power 2 is 1 times 2 is 2. So you have here to be 2. So here, if you put 1 here, 2 times 2 is this. So if you add now, you have 4k. So which becomes 1 over 4. So the value is 1 over 4. So this is actually how to find the true value of k when you are given this kind of problem to evaluate. You understand? So thank you very much. If you have a question anywhere, you can equally drop your worries over the comment section. We are given a random variable x and y with a joint PDF defined as this over this range and 0x1. And we are saying for this to be a true PDF now, what is going to be the value of what? Of k. What we need to do is to integrate this function over this range. Range is given to you. So integral over the range of x over the range of y of that function. That function is this. The x, the y is equals to 1. That's what I did here. So what I did here now was now to bring that of y inside, integrate it first now, then before now integrating with respect to what? To x. So, and at the end of which I have that the true value of x is supposed to be 1 over 4. The challenge we had here was that when I was integrating with respect to what? To x here, respect to x. You now know that here x is already raised to power what? 1. So to integrate now, you add 1 now, it becomes what? 2. We are going to use that 2 to divide the quantity. And that 2 will cancel this what? 4 to give you 2x raised to power 2. So, and if you put this 1 here now, and say 1 raised to power 2 is 1, multiplied by 2 is 2. Put that 1 here, you have this, and at the end, you have this quantity. Thank you very much for your audience so far. Permit me to clean here and then write another thing. Okay, let us take another question very fast. That question says, and I write, it says, number two says, let the joint PDF, let the joint PDF of two-dimensional random variable of two-dimensional random variables x, comma what? Y. B, we have f of x, comma y is given as, we have this x plus y 0. So we now say for, we have 0 less than or equals x less than 1, and then we have 0 less than or equals y less than 1. So we now have what we call 0 x were or otherwise. X were. So the question says, this my marker is becoming a little bit blurred. It's becoming a little bit blurred. So the question says, find the conditional density function. Find the conditional. Find the conditional PDF of y given x. Given x. Okay? If you remember the formula we give for the conditional PDF, we say that the conditional PDF is given as f as of what? Y given what? X. Okay, f of y given x is given as what? F of x, comma y all over f of x. This is what we defined earlier. But we already know this joint PDF, it was given to us. The only one we don't know is the marginal distribution function of what? Of x. But we equally said that our f of x, we see that f of x is given as integral over the range of y of what? F of x, comma y dy. So for me to get this f of x, which is at the denominator, I need to integrate this function now over the range of what? Of y. And for me to do that, what I'm going to do here, I will say therefore, that my f of x is given as what? Integral. The range of y is from 0 to what? To 1. I think it is right. The range of y is from 0 to 1. That's the range of y from 0 to 1. Yes, from 0 to 1. So I have from what? 0 to what? To 1. The function is what? Is x plus what? Y. I will now say dy. So what I'm going to do now is to integrate this function now with respect to what? To y. And by that integral, what it is now going to be is, so I will now, because I'm integrating with respect to what? Y, I am looking at this x now as a constant. And what I'm now going to have there becomes what? I have what? X, y plus. Here it is going to be what? Y raised to power 2 all over what? 2. Then from 0 to what? To 1. From 0 to 1. So what is going to happen is that anywhere I see y, I will put 1. At the end, I will subtract here. So putting 1 here now, x times 1 will give me what? X. Will give me what? X. The sign here is what? Plus. Coming over here and putting 1 here, 1 raised to power 2 is 1, which means I have 1 all over what? 2. I can equally say all over what? 1. So that I can take LCM to be what? 2. I say 2 divided by 1 is 2. 2 times x will give me what? 2 what? X plus. This divided by this is 1. 1 times this will give me this. So I will now come to understand that my f of x is given as this. If my f of x is given as this, please permit me to clean this question and bring my hand up and conclude this question here. Or let me see if I can come here. So I will now say, therefore, my f of this my y given this x is given as, my joint PDF is already given to me as x plus what? Y. I will now say divide by. I can say all over 1 without changing anything. This line means divide by. What I have now is this one. So I have what? 2 what? X plus 1 all over what? 2. This thing now can be written as x plus what? Y all over 1 multiplied by 2 all over 2x plus 1. You understand? So that I'll be able to have what? 2 into x plus y all over what? 2x plus 1. Over this range, over 0 less than or equals x less than 1, and then 0 less than or equals y less than 1 over that particular what range. Okay, so that is what we do for the conditional um, distribution of y given s. If they ask you now for conditional of x given what y, you also say f of x comma y all over f of y. You first of all obtain the marginal distribution, which is exactly what we have obtained here. You understand? So let us drop one question and ask you to look at it at your convenience. Permit me to clean this. Permit me to clean this. Okay. Please, at your convenience, look at this very one to see whether you can get something that is meaningful. That assignment says, okay, let x and y, let x and y be two random variables, be two random variables. Okay. Then for f of x comma y given as this, we have k x y, we have 0 otherwise. Then we have the range here to be 0 less than what? X less than what? 4. And then we have 1 less than what? X less than y, sorry, less than what? 5. Okay? They now say, find the value of x. Find the value of what? Of k, sorry, to make f of x comma y a true PDF. A true PDF. So we still have more other questions that we could have given to you to try, but the size of the video is becoming very large. The most important thing here is just to make you understand how you can navigate your conditional, your marginal, your CDF of a bivariate continuous random variable and see what you can make out from it. Thank you very much for your audience so far, and sorry for the fact that the background is not as bright as possible. The weather is a little bit dark down here, despite the electricity. Please do not forget to subscribe to our YouTube channel and then follow our classes. We are committed to making sure that we bring to you things that can actually add to your values. Thank you very much.